Well, hello everyone, and welcome to the third day of the virtual Xen Summit. Just nothing too much to announce today, except to say that I noticed that there's a number of people on the Design Center website who are not yet verified. So the verification code, if you need it, is Virtual Panda 2021, and I'll paste it here in the chat, just so you have that. And so, without further ado, I will hand over to Bobby.
Great, thanks, George. Get my camera on here. Cool. So, hey everybody. My name is Bobby Eshleman. I work for Vates as a software engineer, and we've been doing a port of Xen to RISC-V. So I'm going to talk about how the privileged architecture of RISC-V works, and then how the hypervisor extension supports virtualizing it. And then at the end, just like a little bit about where the current port, like what the state of it is and where it's going. So just like a little bit of background on what RISC-V is and where it came from. It was developed at UC Berkeley. The ISA right now is governed by the nonprofit RISC-V Foundation, which came about after they released the spec, and interest from the community started to rise, so they developed a governing body. What interests people about RISC-V is that it's completely free to implement and extend. So if you have a chip design that you want to design, there's plenty of open source HDL implementations that you can pull in and develop with, integrate your design with, and you can just send your design to Foundry without any like royalty fees or anything like that. You don't have to pay anything to design with it or work with it, and you don't have to pay to simply use it. And there's a huge open source community on that now, so there's tons of RTL that's available. And there's kind of like a canonical course that are used and are used in silicon right now. So it kind of opened up a large ecosystem there. There's a 32-bit design and a 64-bit design, and they're working on a 128-bit specification. The ISA is very extensible. Everything is pretty much done through extensions, and that also includes the capability for vendors to have extensions, like, for example, like ML acceleration. I think some vendors also have tweaks to the vector extension. This one is super extensible, and we'll be talking about the H extension, which is the hypervisor extension. So it's just some background on the H extension. Where it's at right now is that it's not yet ratified, and there's talk of that being simply because the PLIC, which is a platform level interrupt control, which is a standard specification that's also governed by the RISC-V Foundation. The interrupt controller isn't virtualization aware yet, so it appears that the foundation is simply waiting for that to be specified before they freeze the H extension, just to make sure that nothing has to change. Once it's frozen and ratified, then people are going to want to develop hardware, so you don't want things changing later. And because of that, there's no silicon implementations of the H extension yet. But that said, there is an existing HDL implementation, the Rocket Core, which is developed with Chisel, was extended with the H extension and ran on the FireSim FPGA simulator with the Val hypervisor. So that's been developed and tested and tried. And the really the kind of reference implementation for the H extension is QEMU. That's what the KVM team is developing. That's what we're developing against. And there are hypervisors out there that are developing against. So we're going to talk about the privileged architecture, and then how it's virtualized, because when you're talking about virtualization, really the big part of it is how do you virtualize the privileged architecture for a guest. So the spec defines a hardware thread to be in 3 possible modes, and this is without the agent, so it's just your kind of standard privileged architecture. And hardware thread, we're going to refer to as a heart. Sometimes you'll hear me say that instead, and that's just standard. So you can think of a heart as like a CPU. It's the smallest unit of computation that has its own set of registers. So it can be in one of these 3 modes. You've got machine mode, which is the highest privilege level. Underneath that, you have supervisor mode, and underneath that, you have user mode. And depending on what chip you have and what modes are implemented really defines the profile of the chip. So if you only have M mode implemented, it's a simple embedded, kind of similar like what you think of as an MCU. I think of it as similar to a Cortex-M class processor. You don't have virtual memory, you don't have an NPU for memory protection. You just have a flatly accessible physical address space. The next profile is that if you have MNU implemented, then you have now some level of protection, because you can deprivilege some code, run it in U mode, and limit the physical memory access that it has. And then the type of chips that we're interested in, obviously for the Xen project, is chips that have MS and U mode implemented. And that's when you're expecting a full Unix-like operating system. It has virtual memory. It also has the physical memory access restrictions as well. And each mode, each privilege mode specifically, has its own associated set of CSRs. M mode and S mode have CSRs that are associated with it, and those CSRs are the control and status registers that are where your privileged state resides and where your control of the chip resides. So those are where things like your pointer to your page tables, the paging mode, whether you're allowing user applications to use certain instructions, things like that. And higher modes can see into the lower mode CSRs. So M mode can see into S mode CSRs, but S mode has a limited scope into M mode CSRs. There's some overlap in, so S mode often also reside in M mode, but it's trimmed to what's only relevant to S mode when you're executing S mode code. So looking at kind of what code runs where, I think it's typically pretty clear. Your applications are running in U mode, your kernels are running in S mode, and then there's an SBI implementation that's running in M mode. This is just allow for a little bit more greater portability for supervisor mode code. It's just a pretty simple interface contains things like CPU information, what extensions are implemented, interprocessor interrupts, timer programming, things like that. And between these, you have pretty simple abbreviation. The application talks to the OS through the ABI, and the OS talks to the SBI implementation across the SBI barrier, and that's all done using the eCall instructions. So this is your syscall barrier or your syscall interface, and then your ABI interface. You would call that necessarily a syscall interface, but so that's just the different privilege modes without the hypervisor extension. So here's what it looks like when you have a chip with the hypervisor extension implemented. You still have machine mode doing, nothing's changed there. But now your supervisor mode has been extended with some extra capabilities and extra registers. And so that's called hypervisor extended mode, or hypervisor extended supervisor mode. And then now you've added two modes. You've got virtualized supervisor and virtual user. And this is when you can enable two-stage translation. There's no more direct SBI access. Your virtualized supervisor SBI accesses will trap into the hypervisor, and you don't have the same privileges that you do in HS mode. For hypervisors like KVM, you can still have, if you still have a syscall interface in your supervisor mode code that resides in the hypervisor extended supervisor mode code, then you can still implement that and have user processes. I don't foresee us doing that in Xen because you probably just use like a unique CAD, something like that. That the hypervisor is trying to be, or the hypervisor extension architects were trying to be agnostic to which type of hypervisor the architecture is to support. So this is how they went about that. So HS mode, we're just going to call it hypervisor mode because hypervisor extended supervisor mode is a little bit long to say. Okay, so how does the H extension actually work? We're going to look at the three things that really need to be virtualized in order to support virtualization. That is the CPU, but more specifically the supervisor state of the CPU. How is memory virtualized, and then how is I/O virtualized? So virtualizing the supervisor state. Supervisor mode software has access to a number of supervisor CSRs. They're all prefixed with S for supervisor. M mode CSRs are prefixed with M. Supervisors are things like S status, which sort of the broad state of the chip. S scratch, which is kind of just a register that you can use to store whatever you need for whatever your supervisor mode code is. The kernel uses to back up its thread pointer, and we use it for a similar thing in the port, so on and so forth. So I'm not going to go through all the registers there, but when you have the H mode, the H extension implemented, each Hartman copies of the supervisor registers. One is always kept in the foreground, and then one is kept in the background. So when virtualization is turned off and you're in hypervisor mode, the foreground CSRs refer to your hypervisor state. So those are your hypervisor page tables, the permission. If you're in KVM, the permission is giving U mode code. All those CSRs are in the foreground and in the background, which are accessible to you if you're in hypervisor mode. That copy is reserved for your guest. Now, when you turn on virtualization and you're in virtualized supervisor or virtualized user mode, the foreground CSRs now refer to your virtualized supervisor state. So your virtualized supervisor modes, page tables, and so on and so forth. And background CSRs now refer to your hypervisor state, but they're not accessible to virtualized supervisor code because that would obviously be a virtualization hole. And so the switch between virtualization being on and off, the background and foreground CSRs are swapped. Probably done through like register aliasing or something like that. And the hypervisor mode, specific CSRs that are not part of this copy scheme are always protected. So there's a subset of registers that are really just hypervisor specific that don't need to be copied for a virtualized guest. But they can be emulated, so you can trap on accesses to them and parse the instruction to know what hypervisor mode specific CSRs the guest was trying to access, and therefore you can do that. You use that technique to emulate hypervisors so you can support nesting that way. So just as an example to kind of lay out how the scheme works, in HS mode, your S status register for hypervisor is real supervisor status, and there's going to be another register called the virtual S status, which refers to your guest supervisor state. And then when you switch into virtualized supervisor mode, your S status refers to your guest supervisor state, and the virtual S status is not visible. And accesses to it will cause a virtual instruction exception, allows you to emulate it if you want to support them. The hypervisor's supervisor status is at that point is going to be maintained in the background. If you trap back into the hypervisor, it'll be restored to the foreground. Another important part of virtualizing supervisor state is trap delegation. So by default, all traps are taken to M mode, but M mode chooses like which of those are to be taken by HS mode or supervisor mode. And then your hypervisor extended supervisor mode or supervisor mode code may choose which of those are then to be taken by a lower privilege level. So in our case, we're going to select which traps are to be taken by the virtualized guest. So for example, this is how you can say, okay, well, we're going to, obviously, we want our virtualized supervisor, our guest, to handle page faults for stage 1, but we want to handle the page faults for stage 2. You use trap delegation to configure it that way. Another example is when eCalls are made, if you're in virtualized user mode, you want those to be handled by the virtualized supervisor mode code. You don't want those to trap up to the hypervisor, so you configure it using delegation. So that works as you'd expect it to. So how do you control which virtualization mode you're in? There's an H status register, which is the hypervisor specific status register that contains a previous virtualization mode field, and the S status register contains a previous privilege mode field. And by controlling these two values, you can determine what the mode of the heart will be and when you trap back into, or when you exit your trap handler. So these values are set when you trap into hypervisor mode code to whatever the previous running mode was. And then when you exit from the trap, these values are restored. So for example, if you're in hypervisor code and you want to return to your guest, then you'll set the previous virtualization bit to 1 to say, okay, we want to return to virtualization mode being on. And you'll set your previous privilege mode bit to 1 to say, okay, we're going to return back to the guest when we exit from this trap. And that's done in the S return instruction. And this just lays out the different modes and how you return to either one. So if you have a trap that's in hypervisor mode, you set these bits accordingly to return back to, if you can handle it. That's not happening in the port right now, so I'm not sure if we'll end up doing that or not. But this is how, this just lays out how you would configure your bits when you exit from the trap handler to control the mode of the chip, or the heart. So how is memory virtualized? Pretty familiar scheme. Nothing too crazy here. Just two-stage page tables. The virtualized supervisor mode page tables translate to a guest physical address, and this is referred to as VS stage translation. And then the set of page tables in HS mode translate the guest physical address to your machine address or your host physical address, and that's G stage. Your single stage page tables are given the option of being of having 32, 39, or 48 bits of that virtual address space, and these are referred to in the spec as SV32, SV39, SV48, respectively. And then your G stage tables for the second stage quadruples the amount of addressable space that you have. So you've got SV32 by 4, SV39 by 4, and SV48 by 4. And this is done by just making the root table a 16K block instead of a 4K page. And then that gives you have to extend your index by 2 bits and index into the full 16K. But other than that, it's pretty much the same either way. The page table entries are exactly the same format, whether you're doing stage 1 or stage 2. The only difference is that extra couple pages you need to use for your root, and the usage is a little bit different. Some of the fields you set will be different, but the actual PTE format is exactly the same, which is nice. So how is I/O virtualized with the H extension? You've got 3 different types of interrupts in RISC-V: software, timer, and external. External obviously being for devices. Software interrupts are mediated by the SBI interface. So if your supervisor code wants to issue a interprocessor interrupt, there's a SBI call to do that, and then it's received as a software interrupt on the other heart. And because that's already done via software and via the SBI interface, the hypervisor can just trap and emulate those. These will just be traps on the eCall instruction. Timer interrupts are done in exactly the same fashion, so that'll also just be a trap and emulate type scheme. And because the interrupt controller is not specified to include virtualization support right now, this will just be done via trap and emulation as well. So obviously that's going to be not very performant, but that's where we're at. And that's where all the hypervisors are at until we get that virtualization support at the interrupt controller level. And also, importantly to know, we also need an IOMMU as well to support virtualization, or at least a virtualization aware IOMMU. So just to connect the dots on how all of these parts play together, if you've just created a new guest and you want to jump into guest space, this is kind of what it would look like. You'll initialize your trap delegation using the HE-deleg and HI-deleg registers, which are your trap delegation registers, to define which traps you want your guest to handle and want to handle yourself as a hypervisor. You'll set up your general purpose registers to be what you would expect, or what the kernel would expect a bootloader to hand it, which in this case is you set the heart ID to the 0th register, and then the DTB physical address to the register. You'll map in the kernel and the DTB into the second stage page tables, which exist at this HGATP register. You'll back up your thread pointer in scratch, set the program counter to where you want to return to from your trap handler, or in this case here, it's actually an entry point. And that would just be like the kernel entry point. And then you would set your previous privilege mode and your previous virtualization mode bits, and then exit from a trap handler, which again, in this case, it's a new VM, so it's not a trap handler, but it's code that executes the S-return instruction, and then you'll be in guest mode. So that's kind of how all those components work together to allow you to set up a guest and jump to it. I'm just going to talk about like where the port is right now, just briefly, just to give a kind of a community-wide update on that. Right now, it's about 50% through the start kernel routine of the first guest, which I guess you could call DOM 0, but we'll see when we get there. the HS mode code is pretty functional and plays pretty nicely with Xen-common. Things that are hooked in, so we're doing all the init calls that are done. Well, maybe not all, but we're doing initializing all of the common subsystems for the default config that we have. So this includes like the soft IRQ infrastructure. We kind of primitively support the credit scheduler right now, but we are just kind of stubbing out the timer programmer because we don't really want the interrupt to happen and the scheduling to happen, because it's just easier to debug without that right now because we're at such an early stage. So it's playing nicely with common. P2M is mostly implemented, at least enough to initialize a guest and launch it. But there's a lot of work to be done. Like currently, the OpenSBI emulation is really just enough to lie to the kernel to get it to the next stage. Emulated loads and stores are there, but again, it's just enough to emulate the basic initiation of the interrupt controller from the kernel. There's a lot of stuff that's kind of hard-coded for QEMU vert because there has not yet been like an alternative machine to develop against. So there's no FTD parsing. We'll get that in there when we need it, and no SMP support yet. So we're just compiling with only one CPU configured. So there's a lot of opportunity to contribute, contributing, and but we're making pretty good progress. Every week we're taking down a task. So I've been pretty happy with the steadiness of our recent work on it. I just wanted to leave some links here. Connor posted up a minimal RISC-V build in development. It's going to get merged. I've got an out-of-tree branch that has the initial guest launch in it. It does need to be rebased onto head once the minimal build is there. It's on a much older code base or a much older version of Xen at this point. So that needs to be done. But yeah, so that if you're interested to check out the work that's being done, those links will get you there. And then here's a couple other links for just further live information and resources. So yeah, I've got a couple minutes left, so I'll just open it up for questions. Public chat is very active. Let me go back here.
I was just going to say very quickly that the cross-compiler container is now in the GitLab infrastructure, so anyone can play with either of these branches, even if you don't have some RISC-V hardware to play with. That's as of the start of Xen Summit.
Sweet, and I think that container contains enough to. I think it contains everything except for QEMU. So you can, yeah, exactly like you said, use it to play with the code. Let's see here. So would it be possible for Xen to support RISC-V via trap and emulate on chips that do not support H mode? I believe so. I believe you could. I'm not sure if, that hasn't been planned for yet for the Xen port, but if there was interest, then technically I believe it could be done. Does real instruction decoding for software emulation, or is it nicer? No, I don't think it requires full instruction decoding. We're right now getting by with emulating loads and stores and atomics, and I believe that's what KVM and Xvisor are currently getting away with only doing. I am pretty sure about that. Let's see here. Oh, 7:30 or 7:30 my time. I guess we can move this to a further chat. I don't have the schedule ahead of me, but yeah, we'll wrap it up here, and I'll be around for questions in one of the breakaways or the hallway chat. Okay, thanks, everybody.